So many of you watched my videos and you've seen me do some filter testing, some antenna building. Well, today I'm going to kind of show you how I build one of these filter modules. I'm going to show the basic construction of it, how I put it together, and how I design it using the freely available LC software. My whole purpose for doing this is because I'm making a front-end filter selector box for my SDR radio, but I can also use it with any of my radio receivers. So I'll just go through the basic process of one of the filter modules that I'll use in that and show how I construct the thing from start to finish. So when I come up with a new design for a filter, in this case I'm going to be building a 520 kHz high pass for use on medium wave DXing. It'll filter out everything below about 520 kHz and pass everything above that to the receiver. And I start with using the free version of LC software. You can see all the information of it right there. It's available online in a lot of places. But that's the software program that I start with in any filter design I do. So I'll start in the design window and choose my basic design. In this case it's going to be a Chevy high pass. I'll choose the number of order I want depending on how sharp I want the skirts to be. In this case I've chosen the 7 pole filter so that the pass band slope is pretty steep. Once I've got my basic design down, then I'll plot up the basic schematic, which kind of gives a rough value of where I want to start with choosing components. I'll also take a look at the slope of the filter to make sure it's as steep as I want it. It looks like I want it. In this case, this is the 520 kHz high pass, and you can see here's 510 kHz, here's 520. This will filter out anything below about 510, 520, and pass through everything above that. So once the slope is looking like I like it, and I got the basic schematic out, I'll go through and start choosing capacitors and toroid filters to design and go from there. So once the schematic has got the basic components fleshed out, I'll start designing my toroid inductors using this little program here developed by some other ham radio enthusiasts. You can put the basic parameters in, such as filter, the toroid type. In this case I'm using ferrite FT50 type 61s. You can put in the number of turns you want, or you can put in the induction you need to get kind of a base value of what you're going to use. Now you still need to measure everything once you're all said and done, but this gives you a good starting point and kind of gives you an idea of what you need to roll your own toroid transformers. It makes it pretty simple, and then you can adjust your schematic from that point. So when I start winding a toroid, in this case these are the FT50 type 61 ferrite toroids from, I think they're from Amazon. I prefer to use a 24 gauge magnet wire. You can use thicker or thinner depending on how many turns. If you have a lot of turns on one of these little toroids, you're going to want a thinner wire, probably 26 gauge, maybe even 30. If you're only putting a couple turns, you can even use 22 gauge. Now these filters I'm building are only for receive purposes. I wouldn't transmit more than a couple watts on them because the wire is fairly thin. But basically the toroid calculation program that I showed earlier even tells you how long of a wire you want with a little bit of extra for the leads. So I always take the value they give me, and then I add a couple inches on either end for that. But basically, once your wire's already, you got your length of wire and your toroid, just put the first loop through. I always like to start on one end and finish up on the far end. Some people like to start in the middle and go from either direction. I usually leave 2 or 3 inches sticking out, and I'll take my first loop through, kind of hold it tightly, and pull my second loop through. You got to be careful though when you're pulling your loop through that you don't kink it up, because if you kink it up, it'll mess up the transformer. It'll mess up the inductor. So I just continue on from there. It's kind of like sewing a little bit, but you make sure they're snug. You want to pull them tight. Each time you pull it through, you want to pull it really tight so it snugs up and is close to the ferrite. You also have to be a little careful that you don't rub or scratch the coating on the wire, because this type of ferrite, and some other types can be semiconductors. If they're larger ones, you can wrap them with Teflon tape. I usually wrap the larger type 75 material ferrite toroids with some Teflon tape, so I reduce that chance of getting short in there. But basically, you just go on. It's pretty quick. Once you do this a few times, it's a lot easier. You get the hang of it. It's very fast. So I'll do a couple more turns here. I'll just do one more in this case. And you want to make sure they're snug. I didn't do a great job over here. But once they're all the turns that you need are on the toroid, make sure you spread them out a little bit. Make sure they're fairly even. You don't want them bunched up. It'll cause capacitance, which will affect the values of your toroid. But basically, it's pretty simple. You can do this while you're watching TV. Once you get the hang of it, it's really easy. Once your toroid's finished, then you want to scrape off some of this. Check your values, like I was mentioning earlier, on your meter. And then when you get ready to put the components on the board, you can trim them to the length you need and scrape off the coating. You want to scrape off enough so that when you solder, you don't have soldering issues. After I'm done constructing my toroids, I'll put them on my LCR meter to get the exact values that they are, and I can adjust them turn by turn, either taking turns off or adding turns to get them closer to the values in the schematic. But after they're designed and they're as close as I can possibly get, I'll measure them, write down their values, and then I'll go back and readjust the schematic for the exact values that I've measured in the actual final build of the transformer. Once I've finalized my toroids, my inductors, and I've measured them and I've gone back and modified the schematic, then I'll go to choosing my capacitors. And usually you have to vary them a little bit, but I'll add or subtract capacitors together to get closest to the correct value. So once I've got all my components finalized and gathered together, I'm getting ready to start the assembly. I usually like to use one of these little breadboard PC boards as a starting point. I'll trim it down with either a Dremel tool or nippers like this. They kind of snap off the edges, and it works really well to snip off a small piece very easily, and you can get it to size so that it fits inside your box. So I've already nipped this down. It fits inside my box, and I'm basically ready to start some of the construction. So the box I'm using is this little aluminum, I guess it's an extruded box. It's 89 by 35 by 26 millimeters. It's a model BX37B-3. I believe this is a Hammond case. I'm not certain though. But anyway, this is the basic size I use. It comes with aluminum lid, fits snugly on there. You screw it down. It's pretty RF frequency tight. Nothing's going to get in or out. Before I start the actual construction, I'll drill the holes in the ends to put in my connectors. I like using these F-type connectors because I use 75 ohm coax for all my connections on my radios. My Hammerland SB600 has a 90 ohm impedance, and most of my other ones I either have step up or step down transformers depending on how I'm using it. So I'll use these connectors. They're good for all sorts of frequencies, up over a gigahertz down to long wave and medium wave. It's fine. So once I've selected all the components, built all the inductors, and assembled everything, I have all the components assembled and laid out. Kind of in a mishmash right now, but this is basically what I need to complete the filter along with the PC board, and I'll go from here and start the construction. Until I need each individual part, I like to keep them in this small little Ziploc bag. It keeps everything together and it keeps things from getting lost. Like these capacitors are so tiny, the screws that go into the box, etc. So the next thing I like to start doing then, after I have everything all settled and all the components selected, is to start laying out the components on the board before I solder them. And then to kind of put the inductors in place, put a little blob of hot glue on there so I can keep them oriented and separated to whatever I need them to be. So I'll just let that cool for a second. And once I have all the other parts on, then I will be ready to solder. Now that I got the inductors all positioned on here the way I want them, oriented the way I want, I can start and move on to the capacitors.
I just kind of let the leads for the inductor stick out until I'm ready. Then I'll scrape off the coating on the magnet wire right before I solder. The configuration I'm using, the Chevy format of this, lends itself easily to making it easy where you can have one bus with all the grounding ends of the contacts on, which I'll put a little wire here later on, and then you'll have the capacitors all lined up as one of the other buses for the connection. Okay, so all the basic components are in on the board. All the inductors are hot glued in, and I have the capacitor leads all ready to go to solder. I'm kind of use a dead bug style of soldering. It's not, I'm not the best at soldering, but you get the idea, and you know, it gets the job done. It works. The contacts are good and everything. It's not pretty, but I'm not an artist when it comes to soldering, and I don't have that much experience in it. So now I have I've soldered one side of the inductors to the capacitors, and on the other side I kind of have a little grounding bus which I've made out of a small piece of 22 gauge wire, and I'm going to solder the other side of the inductors to this grounding bus. And before soldering the magnet wire to anything, basically, as I said before, you want to make sure you got all of the coating scraped off the wire, or you're no way you're going to get any bead of solder onto it. So I've gone and added a couple more 22 gauge wires here and here, which will connect to the positive center conductor for the F-type coax connector here and here. So here's the completed filter board. You can see the seven different poles. Soldering job's all done. It's ready to fit and put inside the box. I'll put a little tape over the areas that are not part of the grounding bus, just to make sure that they don't come in contact with the aluminum box. So that'll kind of clean it up a little bit and make sure that contact doesn't happen in the wrong spots. So now that I have everything soldered and with the filter itself, I'm going to drill some holes and mount the connectors in the box, in the ends of the box. I actually center them this way, but I actually have it a little bit higher than center in most of my boxes, so that it leaves a little bit of room under the board to put a spacer or some extra tape to support the filter up. So I'll drill the holes next and put these in. One thing to note when drilling the boxes is that you probably want to have the lid on, even though the aluminum that these are made from is fairly thick. If you put a lot of pressure on it, it can kind of bend it out of whack a little bit, and if you bend it out too much, the top won't fit properly. So I would recommend putting the top on. Makes the box a little bit sturdier. Alright, so now the box is finished being drilled, and it's ready to put the filter board in. I've taken the leads and put them in position for where the connectors will be soldered and or set through these. Put a little solder on this to hold them into place. And in the box I put two little pedestals of hot glue, which will help support this, keep it even and aligned up for the F connectors, which will fit in just like this. So what I'll do for final assembly is just put a couple blobs of hot glue in and set the filter in place. So now I'm going to put a couple of blobs of hot glue in here, fresh blobs. Hot glue gun down. Put
Put the filter in. Make sure it's lined up fairly well inside here. And just set it in place there. Make sure those are lined up fairly well. I mean, they're flexible. And then next, I'm going to thread these through and go from there. Right, so now that the filter is seated within the box, I can proceed to put the F connectors in, and then I will seat the ground wire around the outside here, and I'll screw it up and solder the positive lead to the positive on the F connector. Lastly, I'm going to solder the center contacts to the positive of the filter input. So just put a little blob of solder there. Whoops, that's not good. We'll get that out later though. There we go. A little bit there. A little bit there. And we're done. So now that the soldering is done, everything's all soldered up, it's a matter of testing it. And it's ready to go for testing. I'll just put the cover on, and I'll secure everything down, and I'll give it a test and see how it runs. So here's the filter test setup. Here's the SDR. Here's the antenna switch from no filtering to the filter testing, the 520 kHz high pass filter. And then there's the FM trap over there to eliminate the FM intermod, and then an antenna splitter. So that's basically the same setup I've been using for the other demonstrations and tests. Okay, so here's a demonstration of the filter. In order to best do this to eliminate much of the excess AM band, I actually have a low pass filter on this as well, because I can't see on this SDR, I can't see much of the long wave band, which is this area here, if I don't have the low pass filter on. So basically what you're seeing here is the low pass, what's left of the AM after the low pass, with the low pass in and the 520 kHz high pass filter out. And you can barely hear a 401 kilohertz NDB in the background. But when I put the 520 kilohertz high pass filter in, all the long wave band almost completely disappears. You can still see the AM band here. Looks pretty good. And if I take the filter back out, there comes the whole long wave band with the NDB. And also there's a lot of lightning tonight, which is what these little poofs are in the long wave band. And the filter, 520 kilohertz high pass filter, is also eliminating the static from the lightning. So once again, here's the long wave band and the AM band with the 520 kilohertz high pass filter out. There's some lightning. Put the filter back in, and everything gets nice and quiet. The AM band stays about the same as what it was beforehand. So filter out, some lightning, and the 520 kilohertz high pass filter in. So for a final recap, here's the original diagram based on the needs of the original conceived filter, and here's the original response of that original filter. And finally, here's the final schematic for the filter that was constructed, followed by the theoretical response for the filter that we just tested.